Okay, the third experiment that we have in our lab manual is the assay of anhydrous citric acid. So this is another example of acid and base titration, but your analyte in this experiment now is an acid. The previous one was sodium bicarbonate, which is base. So this is like the opposite. Okay, so the objective is to determine the percentage purity of given sample of citric acid. So citric acid may be one of the components used in drug formulation itself, and it is also naturally available in citrus fruit actually, like orange, lemon. So you can actually measure the concentration of this acid in all those citrus fruit. Later we will see some videos in which they did the experiment on using all these citrus juices. Okay, so basically the principle over here, the assay of anhydrous citric acid is based on titration of anhydrous citric acid with 1 m sodium hydroxide using phenolphthalein as indicator, and the endpoint is appearance of permanent pale pink color. So the indicator used in this acid-base titration will be phenolphthalein. So I think you have used it before. So it is basically colorless at the beginning, and once it turns to the approaching the endpoint, okay, it will start to change color into this so-called like very faint pink color. Okay, if you titrate and overshoot the amount of titrant added, then the color would be like closer to violet. Okay, like very strong pink. So the chemical equation is given by, so you have on the left side is the structure of citric acid. So this structure contain three carboxylic or carboxyl group, C double bond OOH. Or this is also known as tricarboxylic acid, and it will react with sodium hydroxide. Okay, sodium hydroxide to give you the salt. Okay, which is the hydrogen on the COH will get replaced with the Na, and actually the equation suppose the to balance the equation, you actually need 3 moles of sodium hydroxide. So basically 1 mole of citric acid will require 3 mole of sodium hydroxide to form 1 mole of salt. Okay, and 3 molecules of water. So the ratio will be 1 acid, 3 base to form 1 salt, and also 3 molecules of water, or 3 moles of water. So the procedure is basically almost the same as the last 2 titration reaction, in which that you have to prepare the sample in your conical flask or Allen-Mayer flask. So weigh accurately the citric acid first. So the weight given is 2 gram, but when you are using the analytical balance, you actually have to take note up to 4 decimal point what is the exact weight, and then it has to be dissolved in 100 ml of water. So this has to be done in volumetric flask, okay, in VF volumetric flask. So once you have prepared this, okay, you can transfer it into the conical flask and straight away titrate with 1 molar sodium hydroxide using phenolphthalein as indicator. So this sodium hydroxide, okay, has to be prepared earlier, and actually you also have to standardize it. Okay, you need to standardize it basically using the oxalic acid as I think what is available in experiment number 1, okay, the standardization process. So um, the sodium hydroxide, that for this reaction we assume that the concentration is exactly as 1 molar, but if you did the standardization first, okay, you might actually have different value for the concentration. It could be higher, 0.99, sorry, 1.0 something, or it could be lower than 1 molar. So this has to be repeated, okay, at least 3 times, so that you can obtain 3 concordant values, okay, which differs by 0.1 ml. And then each ml of the 1 molar of sodium hydroxide is equivalent to 0.0643 gram of citric acid. So that values will then be used in the calculation later on the percentage purity. So the titer value times molarity of NaOH, just 1. Equivalent weight factor is given by this 0.0643. Weight taken is the exact weight of your sample itself. Okay, theoretically it should be 2.0000 gram, but the actual weight might be slightly different. And the expected molarity is the expected molarity of the sodium hydroxide. Okay, uh, in this case we assume it as 1 as well. So uh, unless you did the standardization, then the numbers would be slightly different. Okay, and you times by 100 to convert it into percentage. So that is on the basically the general procedure for assay of anhydrous citric acid. Now, some example material that I have put on your Google Classroom. Okay, first we watch this together. I'm supposed to show you this during the first experiment, but then again, we watch it now because this is like the general setup on doing a titration. Okay, it also includes some what you call safety precaution as well. So let's watch this.
So the first thing I'm going to do is go through some safety precautions. One is that you may be asked to wear gloves. That's a professor choice or your TA or your teacher. Some individuals like you wearing gloves, others do not in terms of the lab. The one thing that is required is pulling your hair back and wearing safety goggles. The safety goggles could be like these that do not have a complete seal, or you might be required to wear full face goggles. The next thing is maybe you don't have gloves on and you get an acid or a base on your skin or other chemicals. You need to be close enough to a sink that you can go over and wash your hands with copious amounts of water. It's important to know the location of your fire blanket. Now, the titration, you probably won't need that. But the most important thing is an eye wash and a safety shower, and also titrations involve a lot of glassware. So knowing where your broken glass container is and to have a broom and a dustpan to be able to pick up any glass, not with your hands. Last but not least, make sure that you always have pants, closed-toed shoes, and that you follow directions and stay kind of what I call alert in lab, because they will help you get through lab in a safe manner. So these are all the pieces of equipment you're going to need.
So just now she was talking a lot on the safety precaution that you have to take note. Okay, generally about being in the lab and also while doing the titration itself, including on safety goggles, glove. Okay, even if it's okay if you don't wear glove, but you must be nearby to a water outlet in case there is spillage of chemical. You can immediately wash your hands. Okay, so now on to the equipment or the apparatus.
In a standard titration that does not involve a pH sensor. You will need an electronic balance, a weighing boat, and a scupula. That could be if you are going to use a solid acid, maybe potassium hydrogen phthalate, called KHP is the most common example. That would then go into an Obermeyer flask. The other thing that you'll need is you'll need a pipette pump and graduated pipette to measure a liquid acid or base. In this case, we might measure the volume of distilled white vinegar using a pipette pump and graduated pipette. The other option is to use a graduated cylinder, but you'd want that as accurate as you could. The next piece of equipment you're going to need is a burette clamp and a ring stand, because you're going to need to clamp in this device called the burette. This is where your solution of known concentration or the standard goes, or you might standardize the solution that you're putting in here. That's common with the KHP. Use a funnel to fill that burette so you don't spill. The next thing you're going to need is a variety of different size beakers to either be waste beakers, or maybe they're going to contain your known solution or your unknown solution. You'll need an indicator if you're not using a pH sensor to let you know when you've reached the equivalence point. And last but not least, you can use distilled water to rinse down the outsides of the Erlenmeyer flask, or the inside of this burette, or maybe even the inside of this pipette. The first step in the titration is to clean and prepare your burette. You need to make sure that before you add any solution in here or water, that your stopcock is in the perpendicular position to the tip of the entire burette. The other thing is be very careful when you're moving the burette around that you're not hitting the top or the tip on any table or water faucets. The other thing is, if you don't have a sink, you're going to want to have a waste beaker nearby to put all these rinsings into. So the first step, again, is make sure that is in the what's called the off position. You're going to rinse down the inside of the burette with water. You'll want to add about 5 to 10 milliliters of water. And then...
Oh, sorry. I accidentally stopped it.
Is to turn this again very careful. The other thing is, if you don't have a sink, you're going to want to have a waste beaker nearby to put all these rinsings into. So the first step, again, is make sure that is in the what's called the off position. You're going to rinse down the inside of the burette with water. You'll want to add about 5 to 10 milliliters of water. And then you're going to run that water through the tip. If it doesn't start dripping through, kind of give it a shake, and it will end up coming out the bottom due to pressure. The other thing you can do is turn this again very careful and just tip it upside down into the sink. You'll want to do that a few times with water. The next step in titration is to rinse the inside of your burette with the solution that's going to go in it. Typically, it's the standard solution or the solution you're trying to standardize. In this case, I'm using sodium hydroxide. Pour a small amount of that, maybe 20 mils, into a small beaker. Make sure you cap that bottle. The next step is going to be making sure again that your stopcock is closed. And if you can rinse into a sink, you can do that. Or if you have to put your solution into a beaker, then use that. You can use a funnel to fill, or you can try to pour directly from the beaker. I'll use a funnel. Pour about 5 to 10 mils into the burette. Rinse through the tip. Make sure you're trying to remove any air bubbles. And again, if you had to capture this in a beaker, you could do that also. So rinse through the burette tip. Take the burette and take it and make sure you don't hit anything. You roll the solution to coat the entire inside of this burette, and then all of that will need to go into a waste beaker again or into the sink. And then you'll need to repeat that 2 more times with 2 more rinsings of that standard solution. The next step in the titration is to take your solution of known concentration, the type Trent, and pour some in a beaker. Make sure that you don't pour too much more than 50 milliliters, because the burettes typically hold 50 mils, and if you have too much in here, you pour it in, you may overfill the burette. If you're tall enough to fill the burette in the stand, the burette clamp, then just pour it through the top of the funnel. If you're not tall enough, you may have to pull it off of the burette clamp, make sure you don't hit anything, and again, bring it down to your level, and take your solution that you're filling it up with. Make sure that stopcock is closed, and if you're concerned, I would fill it over a sink and fill it slowly. If you're filling it in the burette stand, it's very important that you don't have any of your solution that you're trying to test underneath, in case you do overfill. The other thing to watch out for is that you don't hit the bottom of the ring safe. So you can pour it in. If you don't have to start the titration exactly at 0, what's best is going a little bit past the 0 line on the burette. Take your funnel out, and then grab that beaker that you had your excess rinse solution in from the titrant. Put it underneath, and again, make sure that the tip is filled, there's no air bubbles inside. And that you have then gone below or at least at the 0. If you need to start the titration at 0, you'd have to very carefully make sure that you let enough of the solution out to begin your titration exactly at 0.
So this is what I was talking about. There are bubbles actually trapped inside the burette tip. You have to again open up that, and you may have to tap to release those bubbles. You need the tip of this burette completely filled before you start your titration.
The next step of titration is to record your initial volume before you start. If you took the time to make sure that is exactly on 0, then you would record 0 in your lab book. If not, or on your lab paper, you would record the volume, put some white paper behind it, and you read it at eye level. So for me, I would take this white paper and put it behind it and read the volume with my eyes directly at the level of that solution. And you'd read the bottom of the meniscus.
So this is an example of if you had your meniscus exactly at 0. It's important that in your lab data that you record that at 0.00. This is an example of where your initial volume would not be starting at 0. And for most titrations, that's fine unless you're doing a titration curve. The volume that this is at is 0.59 or 0.60. The big thing with the burette is that you need to make sure you read a hundredth place as an estimated digit. Again, you would record 0.59 or 0.60 milliliters as your initial volume in your lab data table.
The next step of your titration is to prepare this substance that you're trying to analyze. It could be maybe a concentration of an unknown solution, like the concentration of acetic acid and vinegar. Or you could be using a solid that you're trying to find the amount of sumite acid. Typically, what you do first, though, is you do find the concentration of an unknown solution. So make sure that you have some of that solution that you're testing in a beaker, and that you never take the excess of this, putting it back into the original container. That's true for the solution that you're analyzing, called the titrant. It is also true for the solution that you know the concentration of. You'd never want to take any of the excess solution that you have and pour it back into these original bottles. So make sure those get put aside so that you don't use those. The other thing is when you end up with a lot of beakers, you may want to label the beaker so you know what it is. It's very common in chemistry that all solutions are all typically clear and colorless. So on to the next step of getting our solution that we're analyzing, called the titrant, into our Erlenmeyer flask. You can use a graduated cylinder and take your solution and pour a certain amount of it into a grad cylinder, whatever your teacher has asked you to measure. Record that volume in a data table, and then pour that into your Erlenmeyer flask. Or another option, in case the grad cylinders you have are not very accurate, because typically they only read to 1 decimal place, you can use a pipette and a pipette pump. First step, though, is to take your pipette pump and pipette and rinse it with water. Similar to how you did the burette, you'll take that and you'll take that solution and, in this case, water, and just roll it around in that pipette and either dump it into the sink or maybe that waste beaker that you had from before. And you'll need to do that a couple times, usually it's 2 or 3 times. Then you're going to need to go over to the solution that you're measuring. You're trying to find the concentration of, and you'll have to rinse your pipette the same way as the burette by having that solution go in there. Make sure it doesn't go up the top here, that sometimes has cotton up at the top. And rinse that out. And again, you'll need to do this about 2 or 3 times typically. So again, go back to the solution that you're trying to analyze and take that, have that solution end up rolling around to get that solution coat the inside. And again, if you don't have a sink nearby, you end up putting it in a waste beaker. Then, similar to the burette, you need to again draw up a certain volume of that solution. Read the volume the same way you would read a burette. You read the bottom of the meniscus, and in this case, most of these pipettes read to 2 decimal places the same way that the burette does. Record that volume in your data table as your initial volume of your type trend or what you're trying to find the solution's concentration of. So the next step is to transfer what you measured into your Erlenmeyer flask. Be careful moving because air bubbles will go inside, and you might lose some of your solution in the transfer process from here to here. So try to make that a short run between where your solution is being measured from and have your Erlenmeyer flask right next to that beaker so that you don't have to go too far. Then once you've got all that solution in the Erlenmeyer flask, you can then put that underneath the burette. You may have to take the burette and slide it up, because again, you don't really want this tip to get smacked by the Erlenmeyer flask and crack. Put that underneath so that part of the tip is actually facing into the solution. And then the next step is to, usually you'll add some indicator. In this case, we're going to add some phenolphthalein. Because this is an acid, it'll stay clear. Once we start the titration, it'll show a bright pink color, and once that persists, the titration is over.
So that is the general method of doing a titration, basically. So there's a lot of good tips, okay, that she shared, like you have to rinse the burette and the pipette, okay, before actually using it for the titration or transferring any solution. And also like when you are reading the measurement on the burette, okay, it is good to place like a piece of paper behind it so you can see the meniscus clearly, especially if the solution that is in the burette have like very dark color. For example, if you're using potassium permanganate, okay, so that it is quite hard to see actually the reading on the burette, but if you put a piece of white paper behind it, so the measurement can be done easier, okay. So now there are two videos over here in which that they did a titration. For one is for lemon juice and the other one is for orange. So I'll show you just one of the videos, which is titration for the of lemon juice. So actually they are detecting the acid, okay, the citric acid,
we're going to be
the citric acid inside.
of citric acid found in lemon juice, and we're going to be doing that via acid-based titration. Learning the technique of titration will expose us to a variety of very important analytical skills, essential skills required for chemists. First of all, taking a look at our lemon juice, we can see it's full of pith and pips. It needs to be filtered. We're going to be doing that by vacuum filtration. Take a piece of vacuum hose that we've labeled with yellow tape, attach one arm carefully to the side arm of your vacuum flask, and the other to the side arm on the water tap. Place your funnel in the top of your vacuum flask, and then place a sheet of filter paper in the top of your funnel. Turn the tap on. This will create a vacuum inside the vacuum flask. And then pour a small amount of your lemon juice on the filter paper. Just a little bit of the liquid. Make sure you wet the filter paper first. That will get the vacuum started. Then you can pour the rest of your lemon juice in, and you'll end up with filtered lemon juice. Detach the side arm before you turn off the tap. It is most important that you detach it before turning off the water, and you'll then have your lemon juice ready for you to analyze. We'll start by taking a 20 ml aliquot of our sample, and we'll be diluting it to 200 ml. Make sure when you take that 20 ml aliquot that you rinse your pipette with a small amount of lemon juice first. And then once you've completed that rinse, proceed to take your 20 ml aliquot using all the good techniques we've discussed. Up past the mark, clean off the outside with paper towel, drain back down to the mark into a waste beaker, and then do your delivery into your standard flask. Once you've done that, we then complete the dilution by adding distilled water at 20 or 30 ml portions at a time, and give your flask a swirl during additions in order to make sure that the sample is well mixed throughout. As you get close to filling, you can use your wash bottle to get you closer to the mark. And for the last small amount, make sure you use a dropper, pass to a pipette where those last few drops, so that you have the bottom of the meniscus sitting on top of the line. We then mix the standard flask by inversion, like so, and you should do this at least 40 times before proceeding. Now we're ready to complete our acid-based titration. Pour a fresh portion of your diluted lemon juice into a clean, dry beaker. And then using your 20 ml pipette, make sure you rinse thoroughly first, very important, and then take 20 ml aliquot and deliver it into a conical flask or titration flask. You should do this 4 times, and then to each flask, add 2 or 3 drops of phenolphthalein indicator. That will tell us when the reaction is completed. Now we're ready to titrate. Fill your burette with approximately 0.1 molar sodium hydroxide. Make sure you remove the funnel from the top. Make sure there are no air bubbles at the bottom. And then take your initial burette reading to 2 decimal places as best you can. Once you've taken your initial reading, you can then start titrating. You can start adding your sodium hydroxide to your sample. You can start by doing this in a rapid dropwise fashion. As you start seeing flashes of pink develop in your lemon juice, you'll slow down the speed of your additions. Just add a drop at a time and watch the solution. Again, those flashes of pink will get brighter and brighter as you get close to the end. The goal is for you to add a half drop. Get half a drop sitting on the tip of your burette. And then tap it against the side of your conical flask. Take your wash bottle. And then wash down the walls of your flask. Wash all of your titrant down into your reaction. And if the titration has gone strictly to plan, it will be half a drop, takes you from not quite being at the end point to still having a clear and colorless solution to having a faint light pink throughout your solution. Once you reach this point, you can stop your titration, take your reading to 2 decimal places, and you'll know the exact volume of sodium hydroxide required to react with 20 ml of your diluted lemon juice. Now today I'd like to see 3 concordant results, 3 results within 0.05 ml. If you're not sure, ask your demonstrator. If you've got time, they certainly won't mind if you try 1 or 2 more samples before you go. Once you've got those 3 concordant results, you can put your results in the computer and I'll produce a set of class results, which you can use as part of your report. Just finally, before we talk about your report, I often see this color around the lab. This bright fluorescent pink is not the color you're looking for. If you see that in your sample, you have overshot the endpoint. Regarding your practical run, there are a few things to keep in mind. First of all, today's experiment revolved around a chemical reaction between the citric acid and the sodium hydroxide. You're using a known substance, your sodium hydroxide, to find out about an unknown substance, the citric acid in your lemon juice. You can use stoichiometry and your 3-step plan, along with all the tools in your tool belt to help you navigate through the calculations and determine the concentration of citric acid. An extra tip to help you along the way, when we're after the percentage weight volume of citric acid in the lemon juice, all that really means is the number of grams of citric acid per 100 ml of lemon juice. Once you think you've got your result, you can compare that with the class results. If it compares closely, chances are you're on the right track. Good luck.
Right, so that is the examples, okay, of doing a titration for citric acid, but our sample is slightly different, given that from the videos, one of the example videos is using lemon juice, while the other one is orange juice, but in our lab, we use straight away the citric acid powder. So what we're trying to do is actually to determine the percentage purity, okay, of the citric acid, whether it is 100%, 90%, or could be more or less, okay. So regarding your what do you call that report,